Welcome. Yeah, we have finished the gradient descent method. Yeah, we will review what we have done in this week. The gradient descent method was covered in with my lecture note. Now we will see and the lab and go through the review of the gradient descent method. Yeah, gradient descent method can be used to find the x star that satisfies f prime of x star is equal to 0. This is a critical tool in machine learning, and this gradient this method was introduced and upon application was shown. And gradient descent method was summarized in this website with the uh, practice in here. So how it gives us the solution for this minimization problem, and this shows how it works. Okay, and but in English, yeah, we have covered this. So in order to find this minimum value, yeah, we may start uh, in a neighborhood of this point, then use an algorithm to converge to this x star, which can be an optimal solution for the given problem. And gradient descent method algorithm consists of these three steps. And this iterative step is the most important. When we start from the xk, then if slope is negative, then the next point will be found which is closer to x star, and the value of f of xk plus 1 is smaller than f of xk. If it starts from the xk in the other side, but also the same iterative stuff gives us the next point xk plus 1, whose value of the function, the value of the function at this point is smaller than the f of xk. So with these iterative steps, the function value is getting smaller and smaller, and eventually, yeah, we will find the x star that f of x star is equal to 0. Here, this learning rate plays an important role, and if the learning rate is too big, then we may have the iteration which do not converse. But if eta is, but it is more speed, it is speedy. But if eta is too small, then it will eventually converge, but it will take too much of time to converge. So we should be smart to choose a reasonable learning rate eta to find the optimal solution in a reasonable time and cost. So we usually take eta be 10 to the minus 6th power and the interval in this. And we usually choose, in these examples, we choose eta is equal to 0.1 and 0.01, or we may choose 0.001. Okay, anyway, for this example, when f of x is equal to 2x squared minus 3x plus 2, then the x1 was chosen as 0 and eta is 0.1 and eta the epsilon is equal to 10 to the minus 6 power, and then the f prime of x is equal to 4x minus 3, which is equal to 0, which gives the critical point 0.75, and the function was convex downward 2x squared minus 3x plus 2 looks like this. So the minimum value will be given at that point, which is 0.875, which can be verified with the gradient descent method here. When x is equal to 0.75 and the value, the minimum value of the function at that point is 0.875 as it was computed by hand. The iteration took 31 times. As you see here, it converges to the critical point like this. And there was an open problem for your practice with using the same code, and another open problem was asked to you to discuss your output from your practice. Some reference was given, and an application of a gradient descent method was introduced in section 9.2, which was optional. Here, the gradient descent method algorithm was generalized to a multivariable function. The algorithms are exactly the same, except the scalar x was replaced by a vector u, and absolute value of g was replaced by norm of a vector, norm of g, and derivative f prime of x was replaced by gradient of the error function e of u. So when we have the two variable function like this, and we will see this graph, this function is like this, looks like this. So we have the local maximum here and here, and local minimum here and here. Okay, so how you can find the exact value of this critical point, and here the gradient of a multivariable function was introduced, and partial derivative was used. So when you have a function like this, the function f dot gradient parenthesis gives us the gradient of this function. If you change the function like this, then we will have a different gradient. So whatever function you have here, then you will have a gradient easily by this code. Okay, and also the same code can be used for the multivariable function of n variables. In that case, gradient of f is a n by 1 vector whose entries are the partial derivatives of the function with respect to xi, and with those gradients we will use our gradient descent method for a least square problem to find the best fit line for the given data set. In here, we define the error function e of u as this, which is 1/2 of the norm square of the norm of au minus y, which is exactly same as finding the least square solution. When if the error is 0, then au minus 0, the norm of au minus y is equal to 0, which means au is equal to y. So this is a problem of solving a linear system of equation, and then which was the one of the least square problems. Okay, here E of u, if you define E of u and find the minimize this error, and gradient descent algorithm can be used on this E error function and define an error function, and the same gradient descent algorithm was used to find the local minimum here at the point. The critical point was found and local minimum was found. Here U1, U2, U3, U4 converges to this, the critical point, which gives us a local minimum whose value was, this gives us the critical point, and error is very small, and iteration took 118 times to find it. And this gives us the least square solution, because here A and B, A is what A was from this iteration we were able to find A is equal to 3 over 2 and B is equal to 1. So y is equal to 3 over 2 plus 1x was the least square solution that you are looking for. This error was the squared error of these 2 points to this line was smaller when we have these equations. Okay, when we generalize this to a problem of finding a quadratic function that best fit the given data, then the error function was defined in the similar way, and the same iterative method can be used. Okay, the gradient descent method algorithm can be used this new error function with the same condition with more iteration numbers, which gives us the critical point after 4,207 iteration. The critical point was given as 1, 2.5 and minus 0.5. 1, 2.5 and minus 0.5 was given as a coefficient ABC, and so the least square quadratic curve was given as y is equal to 1 plus 5 over 2x minus 1/2 x squared. So that was used. Okay, so gradient descent method is very important to find in the study of AI and machine learning. We will use it in the part of PCA and artificial neural network. Okay, and here is the open problems in this chapter, which is your homework. I think that's the end of the lectures of week 9. Okay, thank you for your attention.